Imagine you want to teach a computer to recognize a handwritten digit, say the number 3. How would you even begin? You could try to write rules like it has 2 connected curves open on the left, but these rules quickly become complicated and break down with different handwriting styles. A neural network offers a different, more organic approach. Think of it not as a rigid set of instructions, but as a digital brain made of interconnected nodes, or neurons. These neurons work together, much like the ones in our own heads, to recognize patterns. It learns from examples, adjusting its internal connections until it can reliably distinguish a 3 from a 4 or an 8. It's a system designed to learn, not just to follow explicit commands. At the heart of this digital brain are its core components, the layers. The first is the input layer. For our digit recognizer, you can picture this as a grid of neurons, each one corresponding to a single pixel in the image of the digit. If the pixel is dark, the neuron activates strongly. If it's light, it remains quiet. This layer doesn't compute anything. It simply receives the raw data and passes it on. Next comes the hidden layer, or sometimes several hidden layers. This is where the real magic happens. The neurons in these layers take the information from the input layer and perform calculations, looking for intermediate patterns like curves, loops, or straight lines. Each neuron in a hidden layer is connected to many neurons in the previous layer, allowing it to weigh different pieces of evidence. Finally, we have the output layer. This layer's job is to give us the final answer. In our example of recognizing handwritten digits from 0 to 9, the output layer would likely have 10 neurons. Each neuron corresponds to one of the possible digits. After all the calculations in the hidden layers are done, the neuron in the output layer that activates most strongly represents the network's best guess. If the neuron for 3 fires with the highest value, the network is confidently telling us, "I believe this image is a 3. The entire structure, from input to hidden to output, forms a pathway for information to flow and be transformed into a meaningful conclusion. The power of this layered structure comes from the connections between the neurons. Each connection has a weight, which is just a number. A high weight means the signal from one neuron has a strong influence on the next, while a low weight means it has a weak influence. Initially, all these weights are set to random values, so the network knows nothing. The process of learning is simply the process of systematically adjusting these weights based on many examples. By fine-tuning these connections, the network gradually gets better at its task, figuring out for itself which features are important for distinguishing one digit from another, all without us ever having to write a single rule about what a 3 looks like. Before we can build our neural network, we need to gather and prepare its food, the data. A neural network learns from examples, so we need a lot of them. For our digit recognizer, this means we need a dataset containing thousands of images of handwritten digits, and crucially, each image must be labeled with the correct number it represents. This labeled data is our ground truth. We will use it to both train the network and later to test how well it has learned. The data must be converted into a numerical format that the network can understand. For an image, this typically means turning it into a flat list of pixel brightness values, a process known as flattening. Let's start by defining our network structure in Python. We don't need fancy libraries for this. We can represent the network using basic Python objects. We'll use the NumPy library, however, as it makes mathematical operations on lists of numbers or arrays incredibly efficient. We can define our network with a specific number of neurons for each layer. For instance, if our images are 28 by 28 pixels, our input layer will have 784 neurons, since 28 times 28 is 784. We might decide on a hidden layer with 16 neurons, and an output layer with 10 neurons for digits 0 through 9. This structure is our blueprint. In this initial code snippet, we create a class for our network. The init method sets up the architecture. The most important part here is the initialization of the weights. We create matrices, or arrays of arrays, to hold the weights for the connections between the input and hidden layers, weights I, and between the hidden and output layers, weights HO. We initialize them with small random numbers. This randomness is important. It ensures that the neurons in the hidden layer will all start by looking for different patterns, preventing them from all learning the exact same thing. The final piece of our network structure is the activation function. If neurons just added up their weighted inputs and passed the sum along, the entire network would behave like a very simple linear equation. It wouldn't be able to learn complex patterns. An activation function introduces non-linearity. After a neuron sums its inputs, it passes the result through this function. A very common choice for this is the sigmoid function, which squishes any input value into a range between 0 and 1. This can be interpreted as the neuron's activation level from off at 0 to on at 1. We can add this function to our class as a separate method, ready to be used during the learning process. Now that our network is built, how does it actually learn? The process is a two-step dance called training, which involves forward propagation and backward propagation. Let's start with the first step. Forward propagation is the process of feeding an input, like one of our digit images, through the network to get an output. The pixel values from the image are fed into the input layer. These values are then multiplied by the weights of the connections leading to the hidden layer. At each hidden layer neuron, all these weighted inputs are summed up, and the result is passed through our sigmoid activation function. This gives us the output of the hidden layer. This process repeats for the next set of connections. The outputs from the hidden layer neurons now become the inputs for the output layer. They are multiplied by the weights_Ho matrix, summed up at each output neuron, and once again passed through the activation function. The final result is a list of 10 numbers, each between 0 and 1, representing the network's guess. For example, if the input was an image of the digit 3, the neuron corresponding to 3 in the output layer should ideally have a value close to 1, while all other neurons should have values close to 0. Initially, with random weights, the output will be complete gibberish. This is where the second step of the dance, backward propagation, comes in. This is the core of the learning process. First, we calculate the error, the difference between the network's nonsensical output and the correct answer, the label for our training image. For instance, if the correct answer is 3, we wanted the output to be 0.0010000000, but the network produced something like 0.1, 0.5, 0.2, and so on. Backward propagation uses this error to figure out how to adjust the weights to do better next time. It's essentially a clever way of assigning blame for the error to each of the connections. The error is first calculated for the output layer. Then, this error is propagated backward to the hidden layer. The math behind this, which involves a bit of calculus, specifically the chain rule, allows us to determine how much each weight in the weights_Ho matrix contributed to the total error. The weights that contributed more to the error are adjusted more significantly. The same logic is then applied to propagate the error from the hidden layer back to the weights_I8 matrix. This blame signal flows backward through the network, telling each weight whether it should increase or decrease to reduce the overall error. This completes one cycle of the training dance for a single training example. The complete training process involves repeating the dance of forward and backward propagation for every single example in our training dataset. Going through the entire dataset once is called an epoch. We don't just do this once. We typically run the training for multiple epochs. With each pass, the weights are nudged ever so slightly in the correct direction. It's like a sculptor slowly chipping away at a block of marble. The initial random block of weights is gradually refined, and the network's internal representation of the digits becomes more and more accurate. The amount we adjust the weights in each step is controlled by a parameter called the learning rate, which prevents us from making adjustments that are too drastic and overshoot the optimal values. Let's see how this training loop would look in our Python class. We would add a train method that takes a list of inputs and their corresponding correct labels. Inside this method, we would loop through each input label pair. For each pair, we perform forward propagation to get the network's prediction. Then, we calculate the error and perform backward propagation to determine the necessary adjustments for the weights. Finally, we update the weights using these calculated adjustments and the learning rate. This loop is the engine that drives the learning, patiently showing the network thousands of examples until the patterns start to emerge from the noise. Once the training is complete after several epochs, how do we know if it actually worked? We test it. This is where the part of our dataset that we set aside earlier, the testing data, comes into play. This data contains images the network has never seen before. We feed these new images into the network using only the forward propagation step. We don't want it to learn from the test data. We take the network's output, find the neuron with the highest value, and see if it matches the actual label of the test image. By doing this for all the images in our test set, we can calculate a final accuracy score, like 95% correct. This process, from understanding the concept to implementing the code, demystifies the idea of a neural network. What we have built is a simple yet functional digital brain. It started as a blank slate with random connections and, through the repetitive process of trial and error guided by backward propagation, it learned to recognize complex patterns. The beauty of this approach is its generality. The same architecture could be trained to recognize other things, from letters of the alphabet to simple sounds. Now it's your turn. I encourage you to take this code, find a simple dataset, and experiment. Change the number of hidden nodes or the learning rate, and see for yourself how this remarkable learning machine adapts.